Hello everyone. Today we are going to start learning about an important machine learning algorithm known as linear regression. So what is linear regression? So linear regression is a mathematical or you can say a statistical technique that is used to find the linear relationship between a dependent variable and independent variable. The independent variables can be more than one. When we have one independent variable, it is known as simple linear regression, and when we have more than one, it is known as multivariate regression. Now, we know that when we plot an xy axis, the x axis is generally considered to be the independent variable and y is considered to be the dependent variable, and we express y in terms of x. So this is somehow the basis of linear regression. This technique is applicable to supervised learning algorithms. So supervised learning algorithms are algorithms where you have to predict a continuous variable. That is something like you have to predict a price, or you have to predict some kind of a number, a numerical value, a continuous value. So when we are trying to predict a continuous variable, we use supervised learning algorithms. And linear regression is one of the most used algorithms while we are doing this kind of an analysis. So we will then look at simple linear regression. So simple linear regression is the most basic model in machine learning, and it models the relationship between independent and dependent variables. So suppose there is an independent variable denoted by x. Similarly, there is another dependent or output variable known as y. X is the input variable, y is the output variable. And we want to build a relationship between these two variables. And suppose, let's just say on the coordinate system, we have a line like this. So mathematically, we represent this line as y equal to mx plus c. We have done this in high school mathematics. So if we are using this same equation again, then we can express y in terms of this equation like beta naught plus beta 1 into x, and we can call this equation 1. So here x and y are the independent and dependent variables respectively. Beta 1 is the coefficient for the independent variable and beta naught is a constant term. And beta naught and beta 1 are the parameters of this model. They are going to help us determine the analysis. They are the parameters. So for simplicity, let's just compare this equation with the standard equation, that is ax plus b. So we can see that the slope of the line is given by the value a, and which in our case is beta 1, and the intercept of the line, that is b, is beta naught in our case. So in a simple linear regression, we want to fit a line that estimates the linear relationship between x and y. So the question of fitting reduces to estimating the parameters of the model beta naught and beta 1. So suppose we have some kind of a data analysis and it fits our model like this. So what we want to do is basically we want to calculate this intercept here, that is beta naught, and we want to calculate the slope of this line, that is beta 1. Once we calculate these two parameters, fitting our model becomes very easy. Let us now look at some more terminologies that are involved in the simple linear regression model. So the first terminology is the hypothesis, or better known as hypothesis function. The hypothesis function. So from our first equation, that is, I'll write it again here, y is equal to beta naught plus beta 1 into x. We can say very easily that y is the dependent variable and it is a function of the independent variable x, and so we can write it like this. The hypothesis variable is written as h of x. So h of x is our hypothesis function, which is a function that best describes the target variable, that is y. So let us just say we have this kind of a block model here, a block diagram. In every data set, we have our training data, and then we push this training data into our ML model, that is the algorithm that we have made. Then we push this data into a hypothesis function. We pass the input value x, and the hypothesis function, which has learned from the ML model, will give us the predicted value of y. So we get this predicted value of y. So this block diagram is very simple to understand. This is our training data. I'll explain it again. We push the training data into our machine learning model. Then our machine learning model pushes the learnings that it has learned in the hypothesis function, and when we pass a parameter x into our function, it gives us the predicted value of y. So this is our basic definition of an hypothesis function. Now we can never get a 100% perfect model. There will always be some kind of an error induced in the function. So we can define the error function for any line, and the regression line is one that minimizes the error function. So suppose we have a line here, and these are some of the haywire data points that we have obtained. And suppose we draw a line that goes through these points like this. Now we can easily see that not every one of these points actually fits the data. Some of them are farther away from the actual line. So now let me depict this like this. So there is a vertical distance, the perpendicular distance. So a regression line is one that will minimize this distance. So when we minimize these distances, what happens is that the error reduces, and it is common sense. We want to have a line that closely passes through all these points. We will never get a perfect line that will pass through all the points. If that was the case, then that would mean that a simple linear regression model is the perfect model, and there would have been no need to adopt any other machine learning algorithms. So the catch is here that we want to take a line that will give us the maximum accuracy and the minimum error as possible. And for that, this is the function of what a linear regression line does. Now, such an error function, we obviously get an error, and there is an error function that specifically defines all these errors. And such an error function is called a cost function. A cost function is used to measure the accuracy of our hypothesis function, and this is done by taking the average difference of all the results of the hypothesis with input from x's and the actual y's. So the formula can be seen as follows. J of theta is described as the cost function, and the formula is as follows. Do not worry about how the formula is derived right now. Understanding how the model will help us in predicting our machine learning tasks is right now more important. It is not important to know how the formula is derived. It can be done easily later after you understand the theme of the model. So this is how the cost function for a simple linear regression model is evaluated. That is the slope of the line, and it is summed over the difference of the distances between these two. As we can see, h theta of x will give us the x coordinate, and yi will give us the y coordinate. And some coordinate geometry knowledge from high school will tell you that this is somehow related to the distance. And what it basically means is that j of theta should be minimum as possible so that the error reduces. And that is the main goal of our model. Now, this is done by another algorithm known as the gradient descent algorithm. Gradient descent algorithm. So a gradient descent algorithm is used to find the parameters so that j of theta is minimized. Our main goal is to minimize j of theta. Once we minimize j of theta and find the parameters, we automatically will get the maximum accuracy that we can get from the model. So the idea is to start from any random point and move in the direction of the steepest descent to reach the minimum. So if we talk about it in terms of generalized models, Like suppose this is a slope, and you are a skiing person, and you are trying to go down this slope. So anybody who has normal skiing knowledge or even normal physics knowledge will understand that to be able to glide through this slope smoothly, you need to have the maximum descent possible. The more the descent, the more easily you can ski down this slope. If the slope is very minimum, then it becomes quite difficult for you to ski down. And that is exactly the principle behind the gradient descent algorithm. We start by taking the point that will give us the maximum slope. So we do this by taking the derivative of our cost function. Another basic calculus knowledge will tell you that on a coordinate system, the slope of any curve is defined as the tangent to that line or the derivative of that line. So this is how we take the slope or the derivative, and the slope of the tangent is the derivative at that point, which will give us a direction to move. So suppose we have a curve like this, and if the tangent is in this way, so we know that we have to move in this direction. So thus if we start from a different point, we may reach a different local minima. Like in calculus, there is a term called local minima and global minima. So at suppose there is a curve of this type, so we get local minima at some point in the curve, but not necessary that they are the least values possible. So if you start from a different point, it is possible that you may reach a point where the value is minimum, but that only might be available for the local value. But our goal is to reach the global minima, because we want to minimize the errors as much as possible. So consider some kind of a plot like this. So this is our slope, and let's just say this is the gradient. So we have to basically find this slope, that is delta h, and to do that we have to find the tangent at this point so that it becomes easy for us to traverse and find the global minima. The cost function for a linear regression with one variable is always a convex function, and it only has one global minima. You will not find more. So gradient descent always converges to the global minimum in this case. Now there is another parameter that will control how large of a step we take downhill during each iteration, and that is known as the learning rate, and it is denoted by alpha. So we have to remain cautious with taking the learning rate. Like suppose we are doing this, and there is a tangent at this point, and we are traversing through this. We are traversing like this. So what alpha basically does is it gives us an idea about how we are going to traverse, how fast we are going to traverse. Like if we take too much of large steps, then we may step over the minimum. Like uh, if the minimum is at this point and we are taking these long strides, then it is possible that without even stopping at the minimum, we will just pass through it. And also at the same time, if we take too many small steps, then it will require a lot of iterations to even reach that point. And nobody wants a slow processing model, right? We are living in a fast world. So we have to take care that alpha is neither too small nor too big, and the gradient descent algorithm is repeated until we actually converge at a point. So at each iteration, one should simultaneously update the parameters. Like this is some basic calculus. So this is our learning rate, and our ultimate goal is to reach theta j. So at each iteration j, one should simultaneously update the parameters. Now there are four assumptions associated with a simple linear regression model, and that is that the relationship between x and the mean of y is linear. Also, for any fixed value of x and y, Y is normally distributed. That is, Y follows a bell-shaped curve. Then the residual error should be uncorrelated with X. So these are the assumptions that go with a linear regression model. Now let us look at the first assumption, that is the linearity. So the first assumption of a simple linear regression is that the relationship between the independent variables and the dependent variables must be linear. Now let us just look at these plots here. So this is a linear plot. Let us just say these are the data points. Now suppose we have a function like y equal to x square. Now we know that this relationship is not linear. This is how the plot looks. So when we are sure that the relationship is not linear, we should use a non-linear model. We should not use a linear model, because without this the linear relationship will give inaccurate predictions for your training data. Like for example, like we have a plot here, and this is how the plot goes. So the second plot shows a non-linear relationship, and thus those training data are not fit for the simple linear regression model. We just cannot show some kind of a simple linear regression model here and expect that we will get accurate predictions. No, our predictions will become very haywire. And once the scatter plot is created for the independent and dependent variables, we have to look for two things. The first is a roughly linear shape where the direction is not important, because the relationship can be positive or negatively collinear. The variables can be positively and negatively correlated with each other, so the direction does not matter as such. And also, if there is actually a linear shape, we want to ensure that there are no outliers in the process. So this is all about linearity. Let us go with the normality now. So the second assumption is that the residuals that result from the regression models should be normally distributed. A normal distribution looks like this. So a normal distribution is a bell-shaped curve where it reaches a certain point of maxima, and it is evenly distributed on both the sides. The area under this curve and this curve right here is same. So a residual is a measure of how far away a point is vertically from the regression line. So like we saw here previously, the aim is to minimize. That is, the aim is to minimize these distances, and that is exactly what the residual is. So a residual will measure how far away a point is vertically from the regression line. And simply put, it is the error between a predicted value and the observed actual value. So as I said, we cannot get 100% correct prediction. And for that, the error between a predicted value and the observed value should be as minimum as possible. So the residual is a measure of that. It will give you the error between a predicted value and the observed value. So once you obtain the residuals from your model, it is relatively easy to test using either a histogram or some kind of a plot. So the residual plot will give you a high density of points that are close to the origin and a low density of points that are away from the origin. So suppose there are these points in the proximity of the origin, and there are some points which are far away from the origin. So a residual plot will give you the idea of these. So if you see any type of exponential curve or any other shape other than a straight line, this means your model is probably not correctly specified, or the relationships are not even linear. So in such a case, it is not wise to use a simple linear regression model, and you also should not try to fit the model in a linear perspective. So this was about simple linear regression, which defined the variable relationship between one independent variable and a dependent variable. So now we are going to come to the more important part, that is multiple linear regression. Multiple linear regression is a regression model which will give you the relationship between the output variable y, and there can be any number of independent input variables x, and we can do a univariate analysis, a bivariate analysis, and a multivariate analysis to predict the value of y. We have seen all this in the EDA lectures. And to build a separate model for each of them, so we have to combine them, and understanding such things will be very difficult. So by using multiple linear regression, we can build models between a variable and its feature variables. So the multivariable regression is mathematically represented in this form. So beta 1 x1 plus beta 2 x2, and we go all the way to beta n xn. And what you should remember here is that x1, x2, x3 to xn are not the variables here. These are values that are already known to us. These are the input values that we are providing. The real variables here are these: beta naught, beta 1, beta 2, and beta n. These are the parameters that will help us determine the model. Like in simple linear regression, we had only this expression. In multiple linear regression, we have up to n parameters, and these are the parameters that we actually have to define. So keep in mind that x1 to xn are not the variables. Now, when we perform gradient descent algorithm for multiple variables, the formula of the cost function doesn't change. The gradient descent equation itself is actually of the same form. We just have to repeat it n times for our n features. So as you can see, the pattern is not really changing. The pattern and the theory behind it is exactly the same, just that we are now doing it for multiple variables at a time. So if we have to define theta naught, so the cost function for theta naught will be of the following form. So this will be I equal to 1 to m, and similarly when we are doing theta 1, we have to replace all the subscripts by 1. So this will remain the same. So you get the idea about how this works. Now there are also some assumptions in multivariable regression. So there is again the assumption of linearity. So the first assumption is multivariate linearity, and the relationship between the dependent variable and the independent variables should be linear. And the best way to check whether the linear relationships are actually present is to create scatter plots and then visualize the scatter plots for a close linearity. If any of the relationship displayed in the scatter plot is not linear, then our model will again give inaccurate predictions, and we will need to run a non-linear regression, or we will need to transform the data, which are tedious processes. Then, multilinear regression also assumes that independent variables are not highly correlated with each other. For example, if we are predicting y and we have independent variables x1, x2, and x3, then x1, x2, and x3 should not be much correlated with each other. Otherwise, it can prove to be very difficult because the coefficient estimates in the models tend to become unreliable. And if the degree of correlation is high enough between the variables, then it can cause the problems when we are trying to fit the model. And one way to detect multicollinearity is by using a method known as the variance inflation factor, or the VIF. So VIF is a measure that it actually measures the correlation and the strength of correlation between independent variables. So the VIF values start at 1 and have no upper limit. So VIF values greater than 5 include potential multicollinearity. So when you are trying to find a VIF value for two independent variables and they come out to be somewhere around greater than equal to 5, then you can assume that these two independent variables can become problematic to you because they have a high correlation between them, and this can cause severe problems while you are trying to fit the model. And when we talk about fitting the model, we come to two of the most important parts when we are trying to make a model. We have to take care of these two models, overfitting and underfitting. So underfitting is a condition when the data clearly shows that the structure is not captured by the model. Underfitting, or even known as high bias, is when the form of our hypothesis function poorly trends the data. So like suppose we have a model here and we have data points here, and suppose we get a linear regression model like this. So as we can see, this model is not really fitting the data. It is quite far away and only hardly 1 or 2 points are even close to the actual model that we have made. So in this case, we say that the model is underfitted. And in other words, which you will usually find, underfitting is the condition when your model fails to predict the training data and the testing data both. Like the model does not predict anything well. Now, the other concept, that is overfitting, occurs when your model fits the training data extremely well. Like suppose there is a model of this type, like almost around 98% of the data, training data, is fit perfectly. But your model performs horribly when you are applying some test data to it. So this is caused when the features are much more and there is no regularization. So training data is predicted very well and testing data is predicted horribly. The accuracy of the testing data is very bad. So this condition is known as overfitting. So we work with the regularization. So regularization works when we have a lot of equally important features. Now the theoretical concepts of regularization are to be studied by us. So a regression model that uses the L1 regularization is also called Lasso regression. This will help us to reduce the problems of overfitting. So Lasso regression adds the absolute value of magnitude of coefficient as a penalty term to the loss function. So that means we have to modify the cost function. So to get rid of overfitting from our hypothesis function, we can reduce the weight that some of the terms in our function carry by increasing their cost. So without actually getting rid of these features or changing the form of our hypothesis, we can instead modify our cost function as follows. So suppose we have this kind of a cost function. So this lambda is the parameter that is actually making use and modifying our cost function. Now we have to understand what this lambda is. So the lambda determines how much the costs of our theta parameters are inflated, and inflation is bad for us. It means that our model will overfit. So using this above cost function with the extra summation sign, we can smooth the output of our hypothesis function to reduce the overfitting. But we have to be careful while choosing the value of lambda 2. So if lambda is chosen to be too large, the first term will be neglected with respect to the second term, and it may smooth out the function so much that it would lead to underfitting. So we have to take care of this. And on the other hand, if lambda is too small, then the second term will be neglected, and thus only the cost of error in prediction will be taken care of, which would again lead to overfitting, and it would just completely bash our purpose again. So when we are when we are trying to evaluate the gradient descent of our regularized cost function that checks both the error in prediction as well as the smoothness of the curve, then applying the gradient descent algorithm to this, we get the following equation. So now our main problem is how to actually set a lambda. So finding the proper regularization parameter is very essential to build correct models that avoid overfitting and underfitting too. So we know that there is a regularization parameter. So how can we actually control the overfitting by deciding its value? We wish to choose a model with low test error and not with a low training error. And thus, to decide the regularization parameter, we take a cross validation method. We first divide all the data sets into two sets, that is training and testing data. And for different values of lambda, we estimate the test error of a model with regularization parameter lambda. So let's say that our k-fold cross validation where the cost of k is 5. Then for each lambda, we are fitting 5 different models and each of them are trained on 80% of the train set and the rest 20% on the test set. So we estimate the test error and choose the value of lambda for which we have obtained test errors. And then we finally train the model with a regularization parameter lambda using the train set and estimate the error of the model with a regularization parameter lambda using the test set. So this is basically how we split the training and testing data, which forms a very important feature of our machine learning models. Then we have another linear regression regularization type called the L2 regularization, and that is known as the ridge regression. So when we are trying to modify the cost function in ridge regression also, we add the squared magnitude of the coefficient as penalty term. So in there we were just taking the mod. Here we will do beta j square. We are squaring the term, and that is how we are actually defining the penalty term. So we now have two clear regularization models, that is the ridge regression and the lasso regression. And as stated earlier, the lasso is a modification of linear regression, where the model is penalized for the sum of the absolute values, that is the mod values, and the ridge regression will give you the squared penalty models. So the key difference between these techniques is that Lasso shrinks the less important features coefficient to 0 and thus removes some feature altogether. We do not actually get that feature. So this works when the features that we have are huge. The number of features that we have are many. So losing one or two features doesn't actually make much of a change in the prediction of the model. Whereas the ridge regression never actually completely removes any feature. So Lasso tends to do well if there are a small number of significant parameters and the others are close to 0. And Ridge works well if there are many large parameters of about the same value. So this was all about how regression models actually work. We will also try to predict some analysis on the car prediction data. We are going to test a model that takes into account the car prediction analysis, and we are going to train our model to test the accuracy using simple regression, multivariate regression, lasso regression, and ridge regression to see our concepts in action. So let us now proceed with our model analysis. So here, as we mentioned earlier, we are going to have the car prediction data set. So we are going to predict the price of cars. We have many parameters that define the car, like the brand of the car, the petrol type, the fuel type, sorry, the mileage it gives, the horsepower, etc. And all these will have a major role in defining the data set. So that will help us in predicting the actual price of the model. So let us start now. So we have to import the data set too. So now let us just import this data set. And now we are going to import our old friends, NumPy, Pandas, Seaborn, and Matplotlib. Now we are going to import the data set in our workbook. So let us just do it using our another of our old friends, the variable that we are always going to use, and say yeah. So our data set has been imported successfully, and as we can see, we are given many features of the car. Like there is the month, the manufacturing year, the kilometers driven by the car, the fuel type of the car, the horsepower, color, etc. And finally, we have the selling price, which we have to predict. So that is our dependent feature, and the other features before it are the independent features. And so as you might have guessed, as there are more than one independent variables, we are going to use multivariate regression analysis here. So let us now print. Yeah, so we now have the type of our column and the number and the columns that are actually there. So selling prices are dependent variable which we are going to predict, and the others are the independent variables which we are going to use in order to predict it. So now we have to perform the data cleaning process. So let us just first look for missing data. So yeah, there are most of our data is false. So there are not much null values here as there are. So let us just verify it using a cleaner and more efficient function, that is the is null.sum that we had even done in the EDA video. And as we get, there are no null values. So it shows that we do not have any missing values in the column. So our task, so some of our job has been saved. Now let us just check the data types that each column has. Let us now print the data types. So we get the data types of every column, and as we can see, for continuous variables we have float 64 as our data type, while for discrete variables we have object category, that is the string, or even the integer as our data type. Now let us perform univariate analysis, that is check each variable individually. So let us start with how many of our percentage as how many of our columns are fuel. So we'll do that by using percentage analysis. So we take this column and we call the value counts function on it. And as we can see, 88% of our cars run on petrol, while the remaining 10% run on diesel, and a very paltry amount of them run on CNG. Let us plot a visual graphic of it. So, fuel type. So, we have a nice little pie chart here, which very clearly shows that petrol is the majority game player here. Now, let us see the exact number of counts that are there for the doors. So the type of cars that have the number of doors. So as we can see, there are around 700 cars that have 5 doors. There are 600 cars that have 3 doors, and there are around 150 cars that have 4 doors. So that is our analysis here. Now, if the column or variable is of numerical type, then we can analyze it by calculating its median, mean, standard deviation, etc. So let us just describe the kilometer driven column, and we can see the mean kilometers driven by a car, the standard deviation, the minimum value, the maximum value, etc. So as kilometer driven is a numerical variable, we easily get the statistical data for such variables, and it will help us in our analysis. Now let us plot our dependent variables line plot. So we can see that the selling price for around 200 cars is 35,000, and maximum of the cars have a selling price of around less than 20,000 rupees. So this is much of the information that we can gather and extract from univariate analysis, and now we have to proceed towards bivariate analysis if we have to make more conclusions. So let us now plot a scatter plot of the selling price and horsepower variable to show what exactly is the relationship between them. So we say PLT dot scatter, and this is our variable, and we do it with the selling price variable, and then I say PLT dot show. So yeah, so this is the general scatter plot of horse variable and the selling price, like how exactly they fare against each other. So we can see on the x-axis the horsepower. So like around cars having 80 to 100 horsepower have a very large density of around 25,000 selling price, and the cars that have a horsepower of above 100 are generally very high in price, that is 25,000 or more. So this is one good analysis that we can make. Now also let us plot the scatter plot of the selling price and gears of variable in a data. So let us say, so we have a scatter plot of the number of gears versus the selling price. So we can see that maximum of this is dominated by cars that have 5 gears or 6 gears. there are very less cars that have 3 gears and 4 gears. So majority of it is going to be concentrated on cars having 5 gears or 6 gears. Now let us plot a bar graph of the transmission with the average value of the kilometer driven. And this can prove to be a very important analysis. So we will use the group by function here with the one variable as transmission, and then we will use the kilometer driven column and say we want the average, so we want the mean, and then we plot the bar graph. Yeah. So now we see that the transmission for automatic and manual plots with a mean value is given here. So this can prove to be another important analysis. So this was some bivariate analysis that we can prove, but as we are trying to analyze a lot of variables here, it is actually the multivariate analysis that is going to provide us more information about what we need to do. So let us just plot the pair plots for some. Sorry for that. And then we say engine. So we are plotting the pair plots to see how exactly all these three variables fare with each other. So as we can see, the selling price with the kilometer driven has a very good relationship. We can make use of it a lot. And the other variables are not really that significant in really under making us understand more about the data. So we are going to create another data plot here that is known as a pivot table, which will give us the value as to what exactly is the number by using a chart. So let us store it in a variable named result. We do it for the doors column, and we specify the gears value for it, and we print the result. And we also want to create a heat map to represent it pictorially so that it becomes easy to understand what the data is visualizing. We use some decorative variables here. Yeah. So we have our pivot table as well as the heat map that is formed. So we can see that metallic and doors and non-metallic and doors is plotted in a table, and we can extract the information out of it. Now we are going to make a complete pair plot with the hue of fuel type. So we can analyze all the variables with respect to how they fare with the fuel type of the car. So this might take some time as there are many variables. So we have our output here, and we can see that for fuel types like diesel, petrol, and CNG marked with their respective colors, how these variables are showing their different variations and how they are actually related to each other. So this is also an important analysis aspect for us. Now, let us come to the data pre-processing part where we will analyze which features are important and which features to remove. So, if we look at the feature year, like the year in which it was manufactured, it does have discrete values, but they range very widely, and as such, they have no relevance to the variable for our model. They do not make sense. So, instead, if we can try to change the variable into something meaningful, such as how old is the car, like we had done in the exploratory data analysis part, or in which month or in which year the car was sold, then it would prove to be a more important feature than just merely describing when it was formed. So this kind of pre-processing is actually used to make the data more meaningful. So let us check the value counts for the month year column. So yeah, we can see that January 2003 has 69 entries, April 2003 has 63 entries, and so on. Now we are trying to split this object by from the underscore that is there. So like to make this into one variable or one record, it is January underscore 2003, and it is not exactly fitting for our model. So we'll just try to split this, and we will build two new features from this existing one. So we will define a new column called month, and then we will take this existing column and we'll make another column called year. If you can recall, we had done something very similar in our exploratory data analysis video where we had split such variables and converted them into more useful features that will help us in predicting and analyzing the data more efficiently. And now that we have created these two features, we will drop this column that is of no use to us, and we will specify it by saying we want to drop the column and fill its place using in place equal to 2. And let us now just see how these new features look. So as we can see, the month year column is completely gone, and instead we have a month column different and a year column different. Now let's check the counts of the year and the months too. So we print df value counts, and we also print df dot month, and as we can see, we get some value so as to how many entries are there for each particular year and for each particular month. Now we come to encoding categories. So as we had said in the EDA lectures, encoding is very important because there are machine learning mathematical models that only work with numerical data types when they are working with predictive analysis. And that is why we need to convert non-numerical data into meaningful numerical data. And to do this, we look at the pandas get dummies method so as to encode some categorical variables. As we know, fuel type is a very important criteria in determining the price of the or the rent of the car. But unfortunately for us, it is in the categorical form. So we encode it into a numerical form so that it is useful for predictive analysis. So we use the pandas get dummies method, and there we specify this column fuel type. Yeah, so it took some time due to this, and as we can see, it is assigning uh, the values. Like for the first row, we can see that the type of the car is a diesel, and that is why it has done the following thing. CNG is assigned value 0 for false, petrol is assigned value for false, 0 for false, and diesel is given value 1 for true. So basically, it is a kind of binary encoding where true is given value 1 and false is given value 0. So whatever type is present, we are getting the value as that particular variable assigned to 1. So now, suppose we want to create dummies for categorical variables and print them. So we store it in a variable called dummies, and then we say pd.getDummies. Then we do it for the color as well, because color also proves to be a good amount of information criteria. We do it for the month, and we do it for the year. And then we print the dummies, and we also concat these created dummies with the original data and drop those categorical columns so that they are no longer used in the original data set, and we get to use these encoded variables in our predictive analysis. So let us just create a new data called encoded df, and we will concatenate these values, the, the dummies values to the original data set, and we will say that we want them as columns, that is axis equal to 1, and then we will also drop them from the encoded df, that is the new data that we have created. So encoded df dot drop, and then we mention which data types we want to drop. Like we drop the fuel type, we drop the color, we drop the transmission, we drop the month, and we drop the year. Then we say axis equal to 1 and in place equal to 2. And now let us just print our new data. So it might take some time because there are a lot of variables and a lot of columns. And yeah, we can see that our data has been encoded in the previous form as I explained for every variable, and then our data has been modified into categorical into numerical data, and the categorical columns have been removed so that it is useful for us in our predictive analysis. So now we need to create some x and y variables so that it is useful for our predictive analysis for defining our dependent variable, and we say y is equal to encoded df, the selling price. This is also known as feature scaling, by the way, and we say x is equal to encoded df dot drop. Yeah. So by dropping the selling price columns, we get the following output. And now we are going to use the sklearn library to create training and test data set. And now we have come to the point where we are going to make our we are going to split the training and test data set to predict the model analysis. And while splitting the training and testing data, the ratio is generally between zero point 0.2 and zero point 0.3. So while using this method, the data is shuffled so that a variable named random state will decide the state we want to keep every time we run the train test split function. So it doesn't just randomly split the data, and for every splitting or every prediction, it keeps the data as same. So the way we do is we import a new library called sklearn. It is also known as scikit-learn. It is a very important library, and without that, we cannot use prediction analysis. So the function that we want to use is present in the sklearn.model selection library, and from that we are going to input a specific function known as train test split. This is a standard function that is always used for splitting the training and test data. So now we define four different variables: the training data for the independent variables, the testing data for the independent variables, the training data for the independent variable, and the training test data for the independent variable. And then we call this train test split function for x, y. We define the test size as 0.25, as we previously mentioned that it is generally between 0.2 and 0.3. It is generally taken between this. These are generally fixed values that you will find most machine learning algorithms use. Even the random state of 42 is a very commonly used value. So we will go with that. It doesn't matter what you take it as long as you take it so that there are no discrepancies later. So we have now successfully split the training and test data, and now we are going to try fitting the model. So first we are going to do simple regression, that is with one independent variable, and for that we will use the number of kilometers driven variable. So first we'll initialize the regression model. So we'll use another library from sklearn.sklearn.linear model, and from that we will import linear regression, and we'll store it in a variable called simple lr, and we'll just normally initialize it. Yeah, so the initialization part is done, and now we have to fit the training data into it. So the syntax for this is we have to use the simple lr variable and call dot fit command on it. Then we have to specify the training variable, the kilometer driven variable inside it, and then the another independent training variable y train. So the confirmation is given to us our linear regression model is properly fitted with the kilometer driven variable as the independent variable with and the y train which is our price. And now we will generate the predictions, the predicted analysis. So this is done by using simple LR dot predict, and we'll use the X test, and then we will print these predictions. So let us run it. So as we can see, we have obtained a huge list of predictions, and all these predictions are in the form of an NumPy array, and we can see that these are the predicted values for our analysis. And let us just see the parameters, the what we had seen as beta naught and beta 1, the coefficient and the intercept. So the way we do it is we call look at the underscore in the syntax, simple error intercept. So we get a simple LR coefficient of minus 0.05 and an intercept of around 15,390. So what we have is we have the value of A as minus 0.05, that is the slope is minus 0.05 and the intercept is 15,390. Now let us analyze the training and testing errors. So this is again done using the sklearn library. So we will just look at our accuracy scores here, and it will not be difficult for anyone to predict what exactly you might not able to predict the actual number, but you will easily be able to understand that our model will not work so good, because despite of having so many independent variables that have a major role in playing a part in determining the price, we have just used one of them. So let us see the training accuracy. So as we can see, we obtained a very bad accuracy value of 32.3%, which is extremely bad. And it is not a surprise that we have such a value, because we have just used one variable to fit the entire model, when in fact there are so many variables that are actually playing a major role. And let's just for a formality see the testing accuracy, which is again going to be quite bad. And yes, as I predicted, it is equally bad. But one important thing to note here is that we have obtained around similar scores, like you can say almost the same score for the training as well as the testing analysis. And this will help us in determining that our model is not overfitting nor underfitting, because we have obtained the accuracy of similar. So it is not happening that the training accuracy is being predicted very correctly and we have a bad testing accuracy, so the model is not overfitting. Neither is it happening this way that the data points are haywire. Now we can obviously say that it is happening because the accuracy is low, but that is happening because we have taken just one variable. So the model is certainly not overfitting. So we can easily say that linear regression is not the preferred way to proceed with this, and we should proceed with multiple linear regression. So again, we have to, as we have imported the module, we don't have to import it again and again. So we define multiple LR as linear regression now. And once we have initialized it, we feed the training data into multiple LR. And now instead of one particular variable, we fit all the variables that are present in the data set. As you can see the difference. And uh, sorry, we'll get an error here because I made a syntax error. Yeah. So now we have fitted the training data properly in our multiple linear regression model with the entire data set. And now let us print the coefficients for each variable. Like we saw, each variable has a different equation, the different value for coefficient, and we have to print it. And we can see that it has been generated into a numpy array. These numbers won't make much sense to us right now, so there is no point in actually discussing about this. So we will proceed with generating the predictions for this model. So we again do it by saying y test predictions is equal to multiple LR dot predict x test. And some values are now there. So we'll interpret the results by again analyzing the training and testing errors. And we'll do that on the training data first. So we get a score of around 89%. And can you see what a great improvement it is? From 32% accuracy, we are predicting the training data with 89% accuracy. And we will do the same thing now for the testing data to see if our model is not overfitting. And as we can see, it is not certainly overfitting because the x test and y test values are around the same thing. But we can improve this with the simple lasso regression and the ridge regression, because it can happen that the model is might overfit because of such a large accuracy value. It can happen sometimes, and to verify that, we will use the lasso and the linear regressions to just verify whether our model is not overfitting. So now from sklearn dot linear model, we import the lasso function, and then we define a variable called lasso lr, lasso. And we have to also define the alpha value, which we say 0.01. Yeah. So we have initialized it, and again we fit the training data into it. So lasso underscore lr dot fit explain and y. Yeah, so I fit it again, and now we'll follow the same procedure to print the coefficients and the intercept. Now we'll generate the predictions. So we'll do it by yeah, we have predicted some values. And now we are going to interpret the result. So to check the regression model training accuracy for Lasso regression. So first we'll do it for the training data set, and we get around the same as we had obtained for the multiple linear regression analysis. I don't even think there is much of a difference there. And now we do it for the test data set, and it is around the same. So let us now cross verify it again using the second type of regularization method, that is the ridge regression. So again we have to import it from the sklearn dot linear model library, and from that we have to import ridge, and initialize is that ridge lr is equal to ridge, and we say an alpha value of 0.00. We slightly decrease the alpha value, and we have initialized it. So now we'll fit the training data. So ridge lr dot fit, now we'll print the coefficients. So ridge lr dot coefficients, ridge lr dot intercept. So now let us generate the predictions. And now we'll do the error analysis. And we are observing that there is not much change from what we had received in the previous two, in the first regularization method as well as the multivariate analysis. Now we are going to talk about another elastic net regression model, which is another type of regularization technique, and we again have to follow the same process to we are basically just following the same techniques to regularize our model and to see whether we have actually overfit it or not. Now we just check our last regularization technique. So there is not, I mean there is no as such great difference, and we can then safely conclude that our model had not overfit, and even the regularization showed that even the regularization technique showed us that the accuracy and the score was simply the same. So we have looked at different regression approaches to deal with our data set. We obtained better results with multiple linear regression than linear regression because of many other independent variables that actually have a significant role in determining the dependent variable. And we found that accuracy for regularized and multiple linear regression were same. And so we concluded that our model wasn't going through overfitting and underfitting, so our model also gave high testing accuracy. So congratulations, you have successfully built a car prediction model, which is your first machine learning project.